All right. Hi, everybody. Welcome back after a couple of weeks hiatus to our high energy seminars. Thank you for joining us. Thank you to our speakers even more for coming and speaking to us. So our first speaker today is Santi Ubach. He is a PhD student at the Autonomous University of Barcelona, working with the high energy astrophysics group. Specifically, he's focusing on QPOs in the very high energy regime in the MAGIC collaboration and trying to understand the origin of these QPOs. Right now, however, he is a pre-doc at the CFA working with Dr. James Steiner, and he's going to be studying black holes and QPOs and working with the Magellan Telescope. Outside of research, he enjoys reading science fiction and training for an Ironman triathlon. Wow, okay. And watching anime and working as a field hockey coach. So, Santi, please take it away.
Yeah, okay, well, thank you so much, Ruto, for the presentation. Well, some of you already know me, of course, Jack, yes. And today I'm gonna just present my master thesis as a pre-doc here, because in the early stages of my research as a PhD, so I prefer to present something more or less finished. It's not finished, this work, but it's on the way of being finished by the rest of the collaborators at ICE in Barcelona. Well, I'm going to present just a study of the S-bearing molecules in high mass star forming regions, and it's an unknown process that we are trying to reveal how it works. Oops. I can move. I cannot. Now. Okay, well, this is the online. I'm going to just talk about a bit from the star formation process for low mass stars and high mass stars, because are roughly different. Where are the birthplaces of these stars is in the infrared dark clouds. The chemistry of these infrared dark clouds are so important. The sulfur problem, this is why I picked this molecule, or well, this element to study the infrared dark clouds and the star formation process. I'm going to explain a bit the aim of this work, then describe a bit the regions. I will talk about, not so extended, but more or less a few interesting things about iron 30 meters. And I think that Rafaela will put or add more things if you want after the talk. I will present the results, discussions, and conclusions, and I talk a bit about my current research with Jack and Marcus Gauck and Luis Fon at the UAB. Well, let's start with the star formation process, and we can see here a nice diagram of how we think that the star formation process occurs. But in this case, we only can, I should say that this is only for low mass star formation, because given the fact that there are a huge variety of physical processes that goes through this process of a star formation, there are two key points: the free fall time and the Helmholtz time. The free fall time is the time required for a dense cloud, a dark cloud, to start with the gravitational collapse and towards the center of this region and create this protostar. That is the three first pictures and of the diagram, and then the Kelvin-Helmholtz time, that is the time needed to ignite the hydrogen of these young stellar objects. For the case of the low mass stars, the free fall time is shorter than the time that the source requires to ignite the hydrogen. So the Kelvin-Helmholtz time is much larger than the free fall time. But for the case of high mass, given the fact that they are more massive, they increase their temperature so rapidly, and they start to ignite their hydrogen before finishes the free fall time. So in principle, when we reach the C panel, the protostar phase, in principle, we think that the massive stars just ignite. So when we ignite something, we start with a radiative pressure. So this radiative pressure starts to just push out this this envelope, so we cannot keep accreting matter. So here we don't know what is happening, so we have to still digging deeper on this field using the chemistry. Well, the birthplace of these massive stars are these dense molecular clouds in the galactic plane, and are dark due to the fact that are dark in the infrared wavelength. And yes, it's the place in which we observe the massive star formation. Well, these infrared dark clouds, such as we see here in this picture, this dark filament. These infrared dark clouds can be starless, contain stars, or the star formation is active. And the chemistry in these infrared dark clouds are pretty different from the interstellar medium, because it's between a few ions or less important of ions and neutral species. And of course, we have a depletion of the gas to a solid phase on dusty grains, icy mantles, and appears some unobservable type of molecules, such as, for example, as molecular sulfur, that you cannot see it. And this is why it's so tricky to understand what is happening inside. To do that, we have to pick at least one kind of element, or we have to think about that. So why sulfur? Why the sulfur problem? Sulfur is just the 10th most abundant element in the Milky Way, but it's important due to these two open key questions. What happened with the disappeared sulfur in the dense regions? What's happening there? And it's possible to understand the astronomical environment with these molecules? Well, of course, yes, it's very important, because sulfur is a kind of element that reacts so fast with a slightly, just change a bit the temperature of their environment. So it's important, because you just start to increase a bit the temperature, you start to see S-bearing species. So for this field is very important. The abundance of the cosmic sulfur is around 10 to the minus 5 in a highly ionized and diffuse regions, but in the infrared dark clouds is only 0.1%. So as I said, depletion, the freezing of the species and the unobserved species, such as molecular sulfur or absorbed species, are important. So we have to try to see what is happening when we increase the temperature, to try to see if this lack of sulfur is due to the depletion and so on in these dense and cold regions. Well, in this work, we studied the chemistry of 3 regions, G14.2, divided into sub-regions, north and south, G34.4 north and south 2, and then G35.2 north. And we try to see if the star formation process is active. And of course, I can spoil you, yes, it's active, but we don't know if it's in the early stages or in the ending point, or where, in which point we are. So we have to look at them. And after that, we try to compare the result of our S molecules with a sulfur model, and also with the low mass star formation region. And well, regions not, this is a mistake, is only a region, the IRAS 1620, that is in a very evolved system, practically in the main sequence. So it's interesting to compare between them to see the evolution of these S-bearing molecules, and try to answer the question of the sulfur problem, and are more or less the following one. Are the abundances of the sulfur are the 0.1% of the cosmic sulfur? Well, more or less are linked between them. So in principle, if we answer the first, we answer the second. Well, we start with the first region. This is a G14 to 225 minus 0.506, hereafter G14.2. In the picture, we see these contours in white. This is an interferometric data. So we only pick on this massive filament here inside the red box in the field north, so the so-called hub north, and the field south in the hub south. But also we have to take into account here, but in the outside the red box, here in the left, we have an ultra-compact H2 region, and it's important to understand how the temperature may change the behavior of this S-bearing molecule. So that's important. Then, in the next region, this is the filament of G34.4. We put in the G34.4 north is the blue box that contains this MM3 core. And in the south region, in red box, we have the MM1 and MM2 cores. And of course, here in the MM2, the people found an iron source. So that is also interesting because with an iron source that is a young stellar object, you may see more evolution, or we can more or less put some constraints in terms of how fast evolves these kind of elements and the system. And this is the last region. We see here the interferometric data of G35.2 north with the different clamps. The clamps are the dense regions in which the gravitational collapse started and the star formation just starts. Is this dark filament, but here we see perpendicular and outflow. So we can say for sure that here in this region, we have an active star formation process. Well, to do this, to carry this work, this research, we use the Iron 30 meters telescope. And this telescope is placed in Spain, in Pico Boleta, Sierra Nevada, and is a very nice instrument because it's a single dish, a 30 meters single dish telescope that has a great sensitivity for weak sources and has a precision of 55 microns and can work and observe in 3, 2, 1, and 0.9 millimeters at the same time. For my work, what I covered is from 95 to 120 gigahertz between lower and upper sideband with a spectral resolution of 0.7 kilometers per second with the 3 millimeters band in this case, which with a beam width of 21.4 to 25.8 arc seconds across the full bandwidth. Well, after this introduction, I'm going to just talk about my results. And in the first quick scopes of the data, we observed, well, my ex-supervisor observed that these three regions presented a lot of S-bearing molecules, a lot of lines of them. And here in this table, we can see all of the, not all, but major part of the SB of the molecules detected. But here we can see all the lines of the S-bearing lines. And yeah, it's easy to understand that G14.2 north, G35.2 north, and G34.4 south are the richer regions in terms of chemistry. So more chemistry means more temperature. More temperature means that something is happening. So it's not only in the gravitational, in the early stages of the free fall time. So we are more evolved than only gravitational collapse. And G14.2 south and G34.4 north are the poor regions. And it means in principle that should be the less evolved regions. Well, here I made the plots of the special distribution, the zero order moment. And this zero order moment has the units of Kelvin kilometer per second. The extension of this panel is more or less because for each source is, well, each source is different, is between 100,000 per 300,000 AUs. So we are not looking the interferometric data. We are not looking through the substructure of the cloud. We are looking from the outside. And it's the intensity of the lines. And here we can see that this is the best region. This is the richest region. And we see a roundy shape in all the S-bearing lines. Well, this one not. This is a kind of molecule that requires an evolved environment. But I also plot this one. Why I plot, Santi, why you need cyanoacetylene? Well, this is important because it's a very stable molecule, and normally it's used to follow the dust distribution. Our dust peak, for example, in all the sources is just plotted as a black cross, and it's more or less peaking always in the peak of intensity of all the sources. Here we see the hub south, and the shape is completely different, and we have an elongated shape. The dust peak and the peak of intensity are not always the same, but yes for cyanoacetylene, and this is why it's our reference molecule. For G34.4, we also see a roundish shape peaking always in the center. The dust peak peaks on the center of the peak of intensity, more or less, except for this one. And here in this panel, I should redo it because maybe I chose a broad range velocity, and maybe constraining putting more on the velocity range of this source, maybe I could see the roundish shape. This is the result of the partial distribution for 34.4 south. Here, this is the iris source, and we see the CS is very, very present in high intensity here and here. But for example, for OCS molecule, is completely different. It's more intense in the MM2 core. That is, we don't know if there is an ISO, a young stellar object, but it's less intense than CS. And also, we observe again, cyanoacetylene fits more or less perfect with the dust peak and the iris source. Then this is the last region that is maybe the most beautiful because it looks like a disk. But here we see just some artifacts in a cross shape. We tried to reduce it, but it could nothing worked. And yeah, more or less this roundish, elongated shape, everything is okay, except for one of these lines, that is sulfate monoxide, that here we see that is not the same. We don't have the same shape, but here, yes, and it's the same. This is the same line. Why is so different? Because I just put some constraints in terms of the velocity range. I just here in this one narrow velocity range because we didn't know if the detection of this line here were due to an artifact, a cloud crossing through our line of sight, or what happened there. And yeah, this is of course a cloud just crossing our line of sight, so this is not important for us. And yeah, more or less is for all the distributions is we can see that more or less we are picking on the dust peak, but remind that I'm not looking the substructure, I'm looking the whole filament or the whole infrared dark cloud. So I cannot resolve the molecules perfectly. I'm just making some kind of a cube overview. Well, after that, I made the column density for nonlinear and linear molecules. And the left graphic plot, you can see that, for example, for G14.2 north, we observe that it has all the molecules that I put in the x-axis, followed by the G35.2 north, and more or less is the highest density, column densities for the G14.2 north. On the other plot is just the abundancy relative to cyanoacetylene, our reference molecule, but with the abundance in the G14.2 north, because it's the only one that has all the SBR molecules. And we can see that G35.2 north and G34.2 I.4 south MM2 presents all the molecules except 34SO, sulfide monoxide, but for 35.2 north presents all of them except this molecule. And yeah, of course, this other molecule. After that, well, we have to answer the question on what happened with the lack of sulfur in these dense regions. To do that, we used our reference molecule doing the line ratios that are strongly linked with the abundances. So this is so important to take into account that. Well, looking to the first region, we should see always a roundish depletion towards the center, and more or less we observe that. But if you remember at the beginning in the description of this region, I said there is a ultra compact H2 region that is placed here in the left that is hitting all of this side. Instead of see depletion more or less uniform, smooth toward the center, we observe something irregular with a lot of presence of non-depleted sulfur species here. For example, this one is easy to see it. Here is a bit tricky to see it, but you can see it. And here, of course, too. Here we can see, of course, again, the non-depleted molecules. The same we can see here in the poorest region. Towards the center is the highest depletion. For G34.4, if we observe sulfide monoxide, if you remember, the intensity we're peaking in this side, but not here. So we observe, yeah, less depletion here. So something is hitting here. I don't know why or what happened there. So it's something that we have to keep investigating. But towards the center, the rounded shape appears in all the panels, and the depletion is towards the center. This is G34.4, and south we observe the same. And this is the last one, that is G35.2 north, is always the same towards the center, following the direction of the filament. But for sulfide monoxide, as I said, we have a cloud here crossing our line of sight, so we don't see here depletion. But yes, but we observe this depletion towards the center in the line, in the line direction of the filament. Well, now it's time to discuss our results, and to discuss it, we just compared our sulfur results with different sulfur models. The first one is the model of the diffuse environments. The middle panel is the turbulence panel, the turbulence plot of the turbulence environment. And the last one is the dense environments model. Looking at my abundance S-bearing species relative to hydrogen, because all of these panels is relative, abundance is relative to the hydrogen, molecular hydrogen, we just can pick one of these molecules and just try in all of these models. And we observe that this one, of course, is not our model. We don't have, for example, CS molecule is in yellow. If I pick CS, is 10 to the minus 9, 10 to the minus 9 here, nothing is happening. So doesn't fit. If we do the same, 10 to the minus 9, CS is the purple line. Practically we touch it, but we don't touch it. So it's not a good approximation. So, well, I'm gonna just pick OCS molecule for the dense environment, and the OCS molecule is in gray, if I'm not wrong. Yeah, it's more or less 10 to the minus 10. If I pick more or less here, I'm around 6, 7, 8 million years. So we should be in between T Tauri phase and the pre-main sequence star or young star object. So it's an evolved but not super evolved system. So we are in between the panel C and panel D of the diagram that I showed shown in the beginning of my presentation. If I, for example, just pick H2CS for G14.2 south, is 10 to the minus 14. So it's something like that. Looking at Turkish bluish greenish line should be something picking around here. So we are in the very early stages of the high mass star formation. But for this one, we are in not so evolved, but more evolved than this one. Another comparison is compare our results with a low mass star formation region, and this one is IRAS 16293, and we know that this source is very evolved, and we just pick this this molecule, this isotope of CS, because it's present in all of our regions, and is a molecular ratio relative to this line. And yeah, avoiding this CS and avoiding 34SO, sulfate monoxide, just look at these ones and these ones. Here, yeah, always 100. Here is 40, and more or less are similar, not so similar, but more or less, let's say similar. Here, 250, and for practically all of the regions is more or less the same or bigger, or they have more presence of these molecules. But on the other hand, we have this much more evolved species that are more complex, are not so easy to catch them. So it means that if you observe this kind of molecules, means that we have a much more evolved system. We observe OCS, H2CS, CH3SH in some of these regions, but the percentage is ridiculous compared with this IRAS source that is huge. So it means that our regions is, for example, for G14.2 north and G35 and G34, the last two, are much more evolved, but for the rest are less evolved. For example, here is a bit different because in the MM2 core, we don't have any young stellar object detected, but it's larger, the abundance is larger with the MM2 core, that we know that there is an IRAS source. And yeah, we can say that our star formation process is active, less evolved than this comparison, but in some of these regions are much more evolved. There are differences between them. The conclusions that I had or obtained of this work is the active star formation process is, of course, active, but less evolved than this IRAS source. I answered the question of our sulfur model because fits perfect with a dense environment, and we are looking through the infrared dark cloud. This is a dense region, so it fits perfect. And then seeing the abundances of SBN species, we can understand now this 0.1% of the cosmic sulfur due to this depletion that we observed with the line ratios in the discussion. So more or less, we did all the things, we answered all the things that we try to understand. Now, the next step for this is the interferometric data and put both observations together, and is now done by my ex-supervisor and new PhD student. So I'm a bit off because I moved to my current research with Jack Steiner since November 2020 to studying the spectroscopy and timing of the stellar mass black holes. And I also am working on black holes, supermassive in the magic collaboration, sorry. And my intention is I will try to figure out the mechanism of these QPOs for both systems, supermassive and stellar mass black holes, with the timing and spectral analogy, with X-rays, gamma rays using Neisser-Neuster, Chandra, and MAGIC, but also maybe we have to talk with Jack about the optical data, but also including Fermilab data and Swift data. And this is my presentation. If you have any question, please.
All right. Thank you, Santi, for a great talk. I think we are actually a little behind on time, and I don't see any questions in the chat yet or any hands raised. So I think we might have to skip questions for now and move on. You can always, well, I think Santi, maybe you also had to leave, so.
Well, I could send at least for 20 minutes more. I
Okay.
think that nobody will complain.
We'll see if there's more time for questions at the end, or otherwise Santi's schedule also has a bunch of openings to meet. So with that, thanks again, and on to you, Peter.
All right, our next speaker is Raffaella Morganti. She is a senior staff astronomer at the Netherlands Institute for Radio Astronomy, Astron, and a professor at the Kaptein Institute, University of Groningen. She started with her PhD at the University of Bologna, followed by an ESO fellowship, and has worked at the Institute for Radio Astronomy, Bologna, the Australia Telescope National Facility, and has been head of the astronomy group at Astron for 8 years. Her career is mainly focused on the study of AGN, and in particular, the properties of their radio emission and the effect that this has on the surrounding interstellar medium. Studying cold HI and cold H1 and molecular and warm ionized. In 2013, she received an ERC advanced grant to explore the role of radio-loud active galactic nuclei in galaxy evolution. For her work, she uses the radio telescopes developed and operated by Astron, but also ALMA, NOMA, and optical facilities from ESO. So thank you, Raffaella, for joining us.
Thank you. Thank you. So let me share the screen. First of all, okay. Can you see all okay?
Yes.
Yeah, okay. Good. So thanks very much for this opportunity to update you on what we are doing, and thanks for being here. So I'm going to tell you the latest work we have done now using the molecular gas, still trying to understand and quantify the impact of jet on the interstellar medium. So I'm going to focus on one case that we have done using ALMA, but in fact, I want to also give you an overview, especially toward the end, of the other work connected with this, the other object that we have done. So, of course, I don't do this alone. Actually, I'm profiting from the work of many people, many collaborators. I should really acknowledge Tom, Clive, and our PhD student, Suma, done part of this work. So, okay, the work is, the work that I will present you, the goal of the work is to understand the impact of AGN, and in particular radio AGN. So that's the famous, infamous feedback, AGN feedback, in which we would have liked to be more advanced by now, given that so many people are working on this, but still there are really many questions that we don't fully answer, we haven't fully answered. So JET, we know that they play a role. I mean, I don't have to tell you at the CFA about the work done using radio emission and X-ray data, the cavity in cluster discovered, and I think this is still the most clear example of AGN feedback or the impact of an AGN. But this happens, as you know, on many tens, hundreds of kiloparsec, so on a large scale. And the idea is that would stop the gas from cooling. What I'm going to argue here is that actually JET can do can help in the AGN feedback, also on galaxy scale. Usually on the small scale, galaxy scale, people tend to favor wind or radiation as producing outflow and clearing the gas from the galaxy. But my feeling, or some of the results that I will show you, indicated that also the jet can do this. And we take inspiration from some of the simulation that I show every time, but I think these are really powerful. So what you see here on the left are a simulation of a jet expanding in a clumpy medium That's a very important ingredient. And if it does, the jet interact with all the clump in the medium already from the beginning. And so although the jet is a collimated flow, actually it can produce a shock bubble around and impact much more gas in the galaxy than just the very narrow jet component. So what the simulation have argue is that in fact the region affected by a jet impinging in a clumpy medium is much larger, as you can see here in this snapshot. And so this goes through a number of phases as the jet evolve. So if this is the case, this simulation, then you can say that the jet start already doing this in the inner part. We are talking about kiloparsec scale, and then as it grows inside the galaxy, may actually join the part that we see on much larger scale. Okay, so that's my kind of starting point. Let me just give you also a look at the simulation and when they run. This is a powerful jet going through this clumpy medium. And as you see, has produced this cocoon around. And so it's not the jet itself that affects the medium, or not only, but also this cocoon of shock gas that expand also in the direction perpendicular to the jet. So, and this happens in particular in the inner phase of the jet life. So when the jet is just born. And so based on all this, we have been studying this young AGN for a while. And of course, we know that jet can produce outflow, have been discovered, found, observed by many, many people in ionized gas. You have shock, you have, so it is obvious that there should be some ionized gas. But the idea is that the ionized gas doesn't carry much of the mass outflow rate. And in the past year, especially with the help of ALMA, but not only, also NOEMA has done a good job, we know that this outflow are multi-phase. We go from cold gas, we have done the H1 part, to the ionized gas, and the most massive component seems to be the one in the cold gas, and in particular in the molecular part. And this is why we have decided in the last years to concentrate on tracing the molecular gas. And this is what I want to show you. So, so that's nice. The problem is, of course, that jet come in different flavor, as you know, radio power, age, they evolve. So if you really want to see whether the simulation actually give a realistic view of what is happening, you need to kind of sample this parameter space. So you need to have objects with different radio power, objects that are very, very young, and then they evolve, still in the young phase, but slightly more evolved. So you need to fill this parameter space. And you see here on the right, some of the object that we have collected so far, a bit with ALMA and recently also with NOEMA. The thing that makes also this observation long is that you need, this is what we have found out by study, you really need to go to higher spatial resolution because you want to trace the gas at the location of the radio to see what happens. And so in the observation that I will show you in a moment, we have used 0.2 arc-second for an object at redshift 0.3. So this requires time and possibly more transition. So it takes time. But anyway, this is our gallery of objects, and the object that I'm going to focus now is this one, this Parkes 0023 radio galaxy that I will introduce you now. So is a young radio galaxy. All the one that I just show you, all the one in this gallery are young radio sources. We know that they are young sources because not only they are small, this is the largest one we have. This is why also is interesting, is about 4 kiloparsec, but they're also peak spectrum. And so we know that they are, if they are peak spectrum, with the peak moving at different frequency, depending on the size, complicated, sorry, but if they are peak spectrum, they are not just beamed objects. Okay, so these are young radio sources studied already in quite some detail. And this object is about 4 kiloparsecs, so has already entered the kiloparsec scale. That is something that we miss in the other. The other are all smaller. It lives in a quite rich environment with other galaxies around. Maybe is a small cluster or a rich group. It's unclear. There are some X-ray observation with XMM, but now we should be getting something much better with Chandra. That's the hope, and I count on Anita for this. So this is a powerful radio source, but also powerful AGN. This is the X-shooter spectrum. So is a powerful AGN in all respect. So it should be blown apart, this host galaxy, the gas in the host galaxy. And there should be gas because there are also far infrared bright. There are young stars, so it's a rich case. And so we have done. Let me just move to the ALMA observation that we have done. We have observed the CO 2 to 1 in this object, as I said, with 0.2 a second resolution. And so what you see here is in orange say the total intensity of the CO that we have detected. So there are about 10 to the 10 plus or minus, because you know all this uncertain conversion factor, but many times 10 to the 9, 10 to the 10 solar masses of molecular gas in this object, spread over about 20 kiloparsecs. So this is a big, nice distribution of molecular gas. It's really a rich medium with some tidal tails connecting some of the companion galaxy. Here we know that they are companion, so, but also the distribution is also a bit offset from the center. So certainly there is more of interaction, and I'll mention later something, but I'm going to focus especially on the region around the radio source. So this contours represent the radio source, the continuum emission of the radio source. Actually, if we do the higher resolution that we can get with ALMA, with the continuum band of ALMA, we can also see the core that was of the radio source. So we can pin down exactly where the core is, where the action is, if you want. Okay, so so there is a lot of molecular gas. That's good, because means that we have the tracer. But the brightest part, as you see, is in the center. It's actually coincident with the radio core. And this may mean that a lot of gas piles up there, or that the conditions are different, the excitation temperature is higher. And this we have found in other objects. I get back to this at the end. Here we have only one transition, so we cannot say, but that's a possibility. So of course you have a line, so you do the kinematic, and this is what I want to show you. Well, no, let me just say, from the distribution you have the brightest part at the core region, while at the lobe we actually see a sort of depression drop that I'll comment more in a moment. Okay, so the kinematic. We were expecting really fast outflow in this robot. Well, no, I was expecting really fast outflow in this bright AGN. But in fact, what we have found is that in the inner part, so I mark here a few regions where I took the profile of the CO, a few regions across the molecular gas. So in the very central part is where we find the broadest profile, but still doesn't exceed about 500 kilometers per second, zero intensity. So that's large, of course, for CO, is disturbed, but is not extreme, let's say. And this is in the brighter part. And you can see also on this position velocity, sorry that I didn't indicate, but was taken in this direction, perpendicular to the jet, to the lobe, the part that is kinematically disturbed. They correspond to this wing. But just to show you that is really something sticking out from the flow of the gas. It's a kind of filament. Then in the region of the lobe instead, we see gas that is, of course, is broad, is 300 kilometers per second, something like that, full width or zero intensity, I would say. There is even an absorption, very, very narrow absorption, though, in the center. But that doesn't really affect the profile. Is about 300. Also in the southern lobe is about 200. So not extreme kinematic. So although the velocity dispersion that I show you here is much higher along the radio structure, is not extreme. Of course, we see velocity dispersion higher also in other regions of the distribution of the molecular gas, for example, here that correspond to this, but is more due to double peak, probably multiple tails due to the interaction. The part that is more disturbed is indeed along or aligned with the radio structure. So just to show you also something else. Sorry to scare you a bit with these channel maps, but these are channel maps across the velocity. The velocity you see here in the corner related with respect to the systemic velocity. And you see the distribution of the gas at different velocity, in a different velocity plane. And the reason why I'm showing you this, while the contour, the purple contours are the radio continuum as indication at low resolution. The reason why I'm showing you this is because actually what we find is that the gas tends to distribute more around the radio lobe. So it doesn't peak at all on the radio lobe, as higher, relatively high velocity dispersion, but it kind of sit around the lobe. So our interpretation of this is that while in the center you have some bright and possibly short gas, at the location of the radio lobe, the lobe instead are pushing away the gas around them. And pushing away because the dispersion we see is higher, but kind of not in an outflow, but just in piling up at the edge. And so, so this is in a way is a kind of scheme that I've stolen partly from one cartoon of Husemann, but in which as the jet and the lobe expand, they are just pushing aside the gas that piles up at the edge. And the jet power has the energy to do this because it's a very powerful radio source. Interestingly enough, that doesn't really affect too much, apparently, the star formation. So this kiloparsec scale source hasn't impacted very strongly the star formation rate of the host galaxy, yet, at least. So, okay, this is what we found. It was a bit of a surprise because, as I say, we expected kind of outflow, but it could be, our interpretation is that when you exit the central, very central region, the density is just too low to produce shock the material, and then give the time to cool again and to reform molecule. So let me put this object in the context of other objects that we have done to see whether we can make dream up a picture of what is going on based on a few objects. So I know it's a bit of a stretch in some cases, but let me show you what we have found. So these are again our object. The green circle are the one that we have analyzed in more detail. So I'm going to spend the last, I don't know, few minutes of this talk. Okay, so so in this very small sample that we have found a few cases of fast outflow. Faster meaning from a few hundred kilometers per second, a bit like the one that I show you in the Sparks 0023, to more than 1,000, like in this object here. This is a position velocity plot of this particular source that is another one of our most powerful one, but very small. It's just a few hundred parsec instead of a few kiloparsec. So we found a few cases of fast outflow. And as I said, we think that the main reason, they are all very small, restricted to very small area. And we think the origin of this outflow is where the gas is very dense, gets hit by the jet, and then dissociate, ionize. But then if the density is high enough, as the time can cool very quickly and reform cold gas molecule, CO, but also H1. We have observed H1 outflow in many of these objects actually. And so, but anyway, this is the faster outflow we have. The most massive is a few hundred solar masses per year. But we have found also outflow in low power radio sources, and this is very interesting because they are much more common than the monster of 10 to the 27, 10 to the 28 watts per hour. So these are two examples. This is something, an object IC 5063 that I'm sure many people in the audience know. We have done a lot of work and even compare with the simulation, the kinematic of the ALMA molecular gas in this position velocity compare with the numerical simulation that I show you at the beginning. So in this case, we could say, okay, yes, the jet must be the one really driving, although a low power jet must be the one doing the damage. And what I'm showing you here at the bottom is something that we just got from NOEMA. Is very interesting, is another very low power radio source where the outflow that is indicated by this position velocity, by this gas, is a few hundred kilometers per second. It's not as extreme as I showed you before, but is located where the radio jet bent. So it's another example of cases where a radio jet, even if not very powerful, can drive this outflow. And that's great because it's what the simulation actually were telling us. So we see some cases of outflow, some more massive than others, but they are all, and that's the point that I want to make, they are all restricted to the sub-kiloparsec scale. All this outflow that we have found are on a few hundred parsec, 500 parsec at most. So, so they affect only that region that we think is the one where the gas is more dense. Okay, not only, but so let's say the gas that really leaves the galaxy is very limited. The fraction of the gas that really leaves the galaxy is very limited. And so we think that the most effect of this outflow is to stir up the medium, introduce turbulence and yeah, moving around the gas because they would drain back most of it like a fountain-like. What this kind of interaction do, though, is also to change to affect the physical property of the gas in this region. So this is, if you have a more transition, you can do this. This is a ratio between, that we have done for IC 5063, this object studied in detail, the ratio between the high transition and the low transition. And you see the region of the disk unaffected by the radio is quite typical of disk of spiral galaxy, very normal CO 3 to 2 to 1 to 0 ratio, very low. While in the region co-spatial with the radio where the interaction occur, we claim the interaction occur, but now we can see also in the physical condition, the ratio is much higher. And so we think this is the effect of the kinetic temperature of the gas much higher in this case. And we see this in IC 5063, but also in this other object where I show you the very fast outflow, much powerful source. Okay, so we have a few cases of outflow, but they are all inside well inside the kiloparsec. So what we argue now is that this happens in the inner region where you have the condition, the density such that you can have this outflow, at least the molecular gas. The ionized gas maybe could be larger, but that's not the one that carry the mass. So we have to decide what is really the impact of this outflow. And then if you go to larger scale, and this is the case of Parks 0023 that I show you, the type of interaction change. And instead of having the outflow, or you still have the outflow, but in the very inner region, also here, in the outer part, you start creating this bubble-like structure that also the simulation suggests. And so you change a mode of outflow, of impact. So you change a mode in a more maintenance-like, so you get a mini bubble that would expand throughout the galaxy. That's a possibility. We will have to check with more data, of course, and affect the host galaxy in that way. So as the source will grow, as the radio source and the radio jet and radio lobe will grow, then is when they are going to affect the rest of the host galaxy. And so at the moment, there is not yet really a strong signature of the star formation rate, for example, impacted by this AGN that was in a way disappointing, but okay. But the main issue here is that the time scale are also very different. So you will need to wait until the source is of the order of 10 to the 7 years, not 10 to the 6 like now, to really see the impact. And actually, this is something that has been suggested also by other people, a group of Arizona, for example, using completely different type of observation, optical observation and simulation, actually, and combining them, comparing them with the simulation. So I'm not sure I've heard any ping, but anyway, this is my summary slide in which, well, it's more a collection of what I've told you. So the fact that we find outflow even of molecular gas. We think many, the one that we find are driven by radio jet, either because we see the effect or because there is not much radiation anyway. They are low luminosity AGN. But we see only on the small scale, there is not much gas leaving the galaxy, so it's more injecting energy turbulence in the medium. And maybe this outflow will not be the type of impact that the AGN gives when you go to larger scale, at least for the radio sources. And so, so in the box down here, I put some thought about this. So the fact that the time scale will need to be considered, also in which stage of evolution your AGN is, certainly for the radio. And this is what we want to do next, to explore whether by taking objects that are still on galaxy scale but larger, what do we see? That's going to be another long-term project, but okay. Of course, the beauty of the radio is also we know that they are recurrent in the life of a galaxy, and this is another part of the work that I'm doing using LOFAR, trying to pin down what are the time scale there. And so how can we connect the two, the impact and how often this happens? And then, of course, there are the X-ray, because if you start building up this bubble, if it's true, maybe we should see, this is maybe the shock are not very strong, because otherwise we will see higher velocity, but still hot gas is there. And so I'm really looking forward to the Chandra observation of two of the objects, the 0023, and also this low luminosity that I'll show you at the end. Maybe should take care of that. And so I hope we can add also that piece of the puzzle in the story. Thank you.
All right. Thank you, Raffaella, for a great talk. We have a couple of questions in the chat, and then after that, we can open up to questions for either speaker. So our first two questions are from Belinda. One is, how powerful is the radio source, for example, compared with high redshift 3CRs?
So the one that I show you, where I focus the first part of the talk, where I told you more, is comparable. It's really 10 to the 27 and something. So it's really a high power source. It's the top, and actually both this one, this Parkes source, and the 0023 that I show you at the beginning are both above 10 to the 27. So they are really powerful source. These are our, we try to sample a large range. I know few objects, but so they are comparable with the 3C.
And her second question is, where is the star formation located?
Yeah, well, would be nice to know, eh? No, wait. So for, where should I go? Maybe so actually for this object, we don't know. We have only an integrated value for the star formation rate. So that would be another thing to explore, but you would need to sample in optical and for the star formation on the same scale as the radio. So meaning you really need a very detailed kind of, because you would expect something happen in the inner pure second.
That other one lines on that other white thing there, too high. Yeah, hard to tell.
So we don't know. There is another object where there are Khalifa data. They know a little bit more, but even there, the resolution is not. You really need now dedicated observation if you want to know the spatial evolution of the star formation, the stellar population, let's say.
Okay. We have another question in the chat from Dan Schwartz. How do you get a velocity or time scale to deduce the power after you estimate the energy content of the jet?
So you mean this jet power, or really the kinetic of the outflow? Because this jet power is, I'm afraid, from the standard formula that I took from the great work done on cavity, like Cavagnolo and things like that. So, yeah, may not be super accurate, but that's definitely, being so powerful, this is going to be order of magnitude, if that was the question.
No, not actually.
No.
I mean, the number 4 times 10 to the 46, for example, exactly operationally, how would I compute that number? I can estimate the energy content in the jet. And strictly speaking, I think the power of the jet is the enthalpy flux. Maybe you just mean the radioluminosity.
Well, that's as a jet power. Sorry, I lost something happened. I lost the screen, but okay. Do you still see my screen?
No.
No.
No, let me, okay, let me stop the sharing. So, so the jet power should be more than the luminosity of the jet. Should be really the energy that includes and that can do the work on the gas to push so much gas. And I acknowledge it's something with a big error, to the velocity that I see, because I see the dispersion at the location of the lobes is relatively high for molecular gas. If you say full width of 200-300 kilometers per second, means that the gas has been moved to those velocity. So the jet power for me is really the energy that the jet can put in it, not the luminosity only.
Okay, yeah, I would agree. But what I thought you said, I may have misunderstood, is that you deduced the velocity of the molecular gas, and then you said that, and the jet has enough power to do this.
Oh yeah, so
but I thought I thought just now you're saying you estimate the jet power by assuming that it does that work.
no, I do the two things separately. I assume I estimated the jet power using this formula taken from cavity. So yeah, kind of assumption, but I assume I estimated that power in that way. And then I estimate, looking at the gas, the mass of the gas that I observe around the lobes, and the velocity at which has been pushed, if it is pushed. I estimate the energy required to do that. And then I compare the two.
Okay,
And
thank you.
typically for in cluster, in cool core cluster, that in a way have many similarity with that system, the jet doesn't have enough power to do that, because typically they have a very low luminosity radio source in the center of cool core cluster. While in this case, I have a powerful radio source. So if I compare the energetic, they are enough. Whether that's the right interpretation is a different matter. I hope it's right.
Thank you.
All right. Bill and Christine, you have a raised hand.
Yeah, first I just wanted to thank Raffaella for just a wonderful talk. We had a couple of questions. The first question is a simple one. The types of objects that you're describing here, the galaxies themselves, are those early type galaxies? Are they elliptical galaxies or spiral galaxies?
They are either elliptical or S0, disky galaxy, but still with dominated by the bulge. They are not spiral.
Okay, and so the first one you talked about, the PKS one that you showed a little hint of the X-ray observations, it had two pieces to it. Is the second piece also on an object at the same distance, or is it unrelated in some way?
I believe the other one is also in that group.
So it's already, so it might well be a cluster or a group or something like that.
Could be the idea, because there are a few redshift. So Clive has done most of the work on this. There are a few objects known around that are part of that group. Cluster, I think, is not really enough for a cluster, but as you know, I'm not a cluster person, so I cannot judge. But the other is on an other companion. And
so then the last question is, so the material that you're looking at is the densest material. Is it, and in some cases it's not moving very fast, you said. And so is it possible that there are other lower density, hotter components that you're not seeing when you look, in these particular regimes that could be moving faster, that there really are, different phases?
No, absolutely. There are. So this object, as I say at the beginning, is a powerful AGN, optical AGN, almost a quasar, you could say. So as a broad line, ionized gas has a lot of ionized gas, and the ionized gas move faster, actually. So is slightly extended in the direction of the radio, in the same position angle as the radio. And there you have lines that reach the 1,000 kilometers per second.
So really quite fast.
Yeah.
And even for the ones that are moving slowly, that you see moving slowly, is there evidence for fast motions in those as well?
No, not always. Not always.
Okay.
Here we have, because it's really a powerful AGN, also from the optical point of view, although there is not much mass associated with the ionized gas, still is moving fast. In other of the objects, especially the one that I show you, one of as the last,
Yeah.
that's a low luminosity AGN, is really a liner. So even if there is something slightly broader in the emission line, there is no fast outflow in ionized gas. So it's a variety. Yeah, when you get to the low luminosity radio, typically you also have lower luminosity optical, unless it's a CFER, of course.
Okay, thank you. And again, thank you for the great talk.
Thanks.
All right, I think that's all the questions for now. So let's thank both of our speakers. If you'd like to meet with any of them, we do have vacancies in their Zoom schedules. So please check the email announcing this talk for that. And hope to see you all next week.
Thank you very much for being here and listen, and for the invitation, of course. Thanks.
Thank you very much, Rafael.